Now that we've learned about complex numbers, I'd like to recall that we had two different forms that we were able to put this complex number in. We could have just listed it as x plus yi, where x, the direction on the x-axis, represents the real part of the complex number, while the distance on the y-axis represents the imaginary part. We refer to that as rectangular form. But then we learned about trigonometric form, not only because it's a different form, but because of the fact that it's going to help us with some operations of complex numbers, namely how to multiply complex numbers, divide two complex numbers, and raise complex numbers to a power. This is going to be satisfied much easier and much faster if we could put it into trigonometric form as opposed to rectangular form. So if we look at trigonometric form, we just need to remember that r cosine theta represents the y-coordinate, and r sine theta is always the y-coordinate on our diagram. Now, if I was to look at this complex number z, remember it's a directed distance in the xy plane that could be drawn as a vector from the origin. So let's keep in mind that if we were on the unit circle, this would be 1, and therefore my x value and my y value would simply become cosine theta and sine theta. So we can see that right now the x coordinate is cosine theta and the y coordinate is sine theta. But notice that that's only if the hypotenuse happens to be 1. So what if I multiply 1 times r? That would increase the size of this triangle, and therefore it would cause my y coordinate to be r sine theta, my x coordinate to be r cosine theta, and therefore my directed distance at my angle theta is going to be r times cosine of the angle and r times sine of the angle. So now just keep in mind that the horizontal axis is the real axis and the vertical axis is your imaginary axis. So we're just going to take a look at what we're able to do when we apply the operations below. So this first time we're going to multiply 1 plus I root 3 times negative 2 root 3 plus 2i. Remember, the way that we're doing that is simply by distributing each term in the first to each term in the second. Okay, so this simply becomes negative 2 root 3 plus 2i minus I times 2 root 3 times root 3. So keep in mind, when I multiply root 3 times root 3, that just simply gives me 3. So 3 times negative 2i gives me negative 6i. And finally, when we multiply I root 3 times 2i, that's going to give me plus 2 root 3i squared. Okay, well now let's keep in mind that I squared is in fact negative 1. So since I squared is negative 1, then really what we're doing is we're combining our like terms of negative 2 root 3 and negative 2 root 3, which gives me a total of negative 4 root 3. And now we're combining our like terms of 2i and negative 6i, which gives me the answer of negative 4i. And therefore, that again is in rectangular form. So I started with two numbers that were in rectangular form, multiplied them, and notice that when we multiplied them, we ended up getting a new complex number, again in rectangular form. Take both of these complex numbers now, and I'd like to convert them individually into rectangular form. Now, if we convert this first one into rectangular form, we should realize that the x coordinate is 1 and the y coordinate is root 3. For the second one, the x coordinate is negative 2 root 3, or the real coordinate, while the y coordinate is 2. Secondly, we should recognize that if we were to plot these, this first point, or this first complex number, would be some number in quadrant 1. We should also recognize that this second point would be some value with a negative x and a positive y, which would occur in quadrant 2. So now let's go ahead and use our formulas to find what our R values and our theta values are. Okay, so first of all, x squared or R is equal to the square root of x squared plus y squared. So that radicand is just 1 plus 3 or 4, so the square root of 4 tells me that the R value is 2. If we now go over to the other side, we get that the R value is equal to, again, the square root of, but now it's the sum of the squares of those two values. So negative 2 root 3 squared plus 2 squared. And now we can see that when we square 2 root 3, we get 4 times 3 or 12. While over here, 2 squared is 4. So 12 plus 4 is 16, and the square root must be 4. We can also use this information in order to find our theta, keeping in mind that tangent of theta is equal to the y coordinate over the x coordinate. Well, we know the tangent of theta is equal to root 3, and therefore, because of the fact that this is going to be in quadrant 1, we know that theta is pi over 3. So we could say pi over 3 or 60 degrees, depending on whether we're dealing with radians or degrees. If we go over here, we get the tangent of theta is equal to 2 over negative 2 root 3. And we could cancel the root or the 2's and multiply by root 3 over root 3 in order to rationalize. And now notice that that gives me the tangent of theta is equal to negative root 3 over 3. And therefore theta is again a pi over 6 angle, but it's in the second quadrant, and therefore it's the pi over 6 angle in the second quadrant. So 5 pi over 6 or 150 degrees, again, depending on whether or not we're in radians or degrees. So that must mean that for the first number, what we're really doing again is we are multiplying okay, and we're now going to multiply 2 times cosine theta plus 2, I'm sorry, I should say 60 degrees. So we're dealing with R equals 2 and theta equals 60 degrees. And so this becomes 2 cosine 60 degrees plus 2i times sine of 60 degrees. And that's now the first number. Now if we multiply by the second number, that's going to be 4 cosine of 150 degrees plus 4i times sine of 150 degrees. And now that we have, again, this same basic scenario, except that now it's in trigonometric form, notice we can still do the distributive property. We can distribute again by just multiplying each term in the first to each term in the second, and therefore multiply to get these 4 terms. So let's work that out. So the first one gives us 8 times cosine of 60 degrees cosine of 150 degrees. For the second one, we get plus 8i, and now we get cosine of 60 degrees sine of 150 degrees. For the third one, we get 8i, again, an imaginary number, and I guess I should put that in pink as well so we can keep track of these two types. So now we're multiplying these two numbers, which gives me 8i sine of 60 degrees cosine of 150 degrees. And finally, when we multiply the last terms, we end up getting plus 8i squared times sine of 60 degrees and sine of 150 degrees. So we did the same distribution, and although this looks like it's a lot more complicated, I'd like to focus on doing a little bit more work here to try to simplify this. First of all, I should realize that every term has an 8 out in front. So I could factor out that coefficient of 8. I'm now going to group together the imaginary parts and the non-imaginary parts. So let's first deal with this, which we get cosine 60 degrees, cosine of 150 degrees. And then over here, this is going to be a real number as well, except that now notice I'm dealing with I squared. So since this term has an I squared, I know that I'm now subtracting sine of 60 degrees times sine of 150 degrees. And that takes care of the first part. For the second part, we now know that we're going to have plus I times something, because now both of these terms are going to have imaginary parts. So we now see that this is going to be cosine of 60 degrees, sine of 150 degrees, plus sine of 60 degrees times cosine of 150 degrees. Now keep in mind that we're still trying to simplify this first problem where we multiplied these two complex numbers together, but all we were expected to do was distribute and combine the real parts with the imaginary. Now we've done this work to convert each of those numbers into trigonometric form so that we can now multiply those two numbers together. But now let's simplify and realize that there is going to be a very nice shortcut to be able to get to this point. Because notice that 8 follows us along here. But now let's take a look at each piece inside. This formula right here is the formula used for cosine of a sum or a difference. This is simply going to be cosine of the sum of 60 degrees and 150 degrees. While this second piece, when you take a look over here, this, because we see cosine times sine, is going to be the sum formula for sine. So we're now going to get I times sine of 60 degrees plus 150 degrees. And therefore, if we look back to here, let's take a look at our original form and realize where the 8 came from. The coefficient of 8 came from the fact that I simply multiplied the two R values, while the new angle came from adding together the angles of 60 and 150. So in fact, in one step, we could have actually just combined this in order to recognize that this form is going to be our R1 times R2 times cosine of theta 1 plus theta 2. So I just simply added the two angles. And as for the imaginary part, that would be sine of, again, the sum of the two angles, theta 1 and theta 2. Or in other words, we could rewrite it as R1 times R2, and then use the word cis for our shorthand notation, and get theta 1 plus theta 2. So in other words, in order to multiply two complex numbers together, we're simply multiplying the R values and adding the theta values. And therefore, our final result becomes 8 cis of 210 degrees. Now let's just verify that this in fact is our solution. Okay? If that's our solution, keep in mind we've already done this problem. We already saw originally that the solution was negative 4 root 3 minus 4i. So now let's just switch back and find out if sure enough that is the answer. Since this is r cis theta, my new final answer, let's just convert that back into x and y coordinates. Notice that our x coordinate is going to be 8 times cosine of 210, while my y coordinate will be 8 sine of 210. Okay, well, 210 degrees is in the third quadrant. So we just need to realize that x is equal to 8 times 210 degrees is the third quadrant answer. So cosine is negative root 3 over 2, while y is going to be negative 1/2. And therefore, if we rewrite this in trigonometric and rectangular form, we find out that that answer is negative 4 root 3 minus 4i. And so both of these are equivalent to each other, and therefore what we've learned is a product rule that allows us to multiply these two numbers together. So let's do one more example and determine what and come up with a much faster method. Let's demonstrate the formula that we just learned about multiplying two complex numbers in trigonometric form. We learned that all we need to do is multiply the radii to get 3 times 2. And then in order to find the corresponding angle, we simply have to add the two angles together. And therefore, the final result becomes 6 cis of 180 degrees. And therefore, look at how fast it is to multiply two complex numbers in trigonometric form. If they weren't in trigonometric form, we would have to do the expansion and distributive property, but now we've got a much quicker method of doing so. Now we just want to recognize that this is the same thing as 6 times cosine of 180 degrees plus I times sine of 180 degrees. Now when we look at this, we can see the cosine of 180 is simply negative 1. Sine of 180 is 0. So what we really have here is 6 times the complex number negative 1 plus 0i, which is now a real number again. And therefore, 6 cis of 180 is the same thing as simply negative 6. And this should make sense because if you think about 180 degrees, that lies on the x-axis, which is our real axis. So this is just saying move 6 units along the angle of 180, which is the same thing as moving negative 6 units on the x-axis. So let's take a look at what happens when we take a quotient of two complex numbers. Now, in a problem where we want to divide complex numbers, keep in mind the only way to do so, to write back in rectangular form again, is to multiply by the conjugate of the denominator in order to get rid of the complex number in the denominator. So we get negative 2 root 3 minus 2i. And if we multiply by that in the numerator and denominator, then that's going to eliminate the imaginary number in the denominator. So now it's just a matter of expanding the numerator. Notice that in expanding, we do get a couple of complex numbers, or a couple of imaginary numbers will combine. And we also get an I squared, which remember is the value of negative 1. So now let's take care of the denominator. In the denominator, we see the same thing, but notice the nice part about the denominator is not only are there a couple of imaginary numbers that combine, but they're also opposites, so they will cancel. And likewise, there's another I squared that has the value of negative 1. So if we were to simplify now, this would end up giving me 2 root 3, or negative 2 root 3 on top, minus 8i, minus 2 root 3 times negative 1, which is plus 2 root 3. And notice what happens there is that the denominator or the numerator has two radicals that cancel, which means when we divide on top, we get, or on the denominator, we get 12 plus 4 because -4 times -1 is 16. So -8i divided by 16 gives me an answer of -1/2 I. And that right there is the answer when we divide those two complex numbers. Now I'd like to convert this into trigonometric form. All right. So if this is in trigonometric form, we need to find our R value and our theta value. If we look at the X and Y coordinates of this point, we see that the X coordinate is 0, or the real part, while Y has a coordinate of -1/2. So in applying our formula for finding R, we know that R is 1/2. But now if we take a look at tangent theta, notice the tangent theta is Y over X, and that's equal to -1/2 over 0. That's undefined. So now we just got to think about, where is this -1/2 I located? I know that tangent is either undefined at pi over 2 or at 3 pi over 2. But when I look at -1/2 along the imaginary axis, that's just going to be straight down because it's imaginary. That's an angle of 270 degrees, and therefore theta is 270 degrees. So how does that shape look when we end up looking at the division or the quotient of two values or two complex numbers in trigonometric form? Now, if we were to divide these two complex numbers again, we already calculated earlier what the trigonometric form of those two separate numbers were, and we've just rewritten it down below here. And so now we're going to try to divide these using some other rule similar to the product rule. Now, if we're correct, knowing that R is equal to 1/2 and theta is equal to 270, then this should turn into 1/2 times cosine of 270 degrees plus I times sine of 270 degrees. Now, I suppose we could already see that what we've done here in order to get 1/2 is that we divided the R values. 2 divided by 4 is 1/2. If we were multiplying them, that's why we took the product of the two R values. So it looks like all we're going to do to calculate this is take one R value and divide by the other R value. But remember, when we were dealing with the product of two complex numbers, we added the angles to get 210 degrees. Well, let's take a look at what happened if we were to subtract the two angles. Notice that we get 60 degrees minus 150 degrees. So if we were to do that and say theta 1 minus theta 2, and we do the same thing for the sine value or the imaginary component, giving me theta 1 minus theta 2, then notice that that would give me -90 degrees. So notice that 60 degrees minus 150 degrees is actually -90 degrees. We expected up at this corner up here to be positive 3 pi over 2, or positive 270 degrees. But we should also realize that we could get to that same angle by going -90 degrees. So -90 degrees is in fact the same thing as 270 degrees. And therefore, by this formula, we can see that the formula gives me 2 divided by 4 times cosine of 60 minus 150, which is -90 degrees, plus I times sine of -90 degrees. But notice -90 degrees is coterminal to 270 degrees. And therefore, by using our formula again, our answer simply becomes 1/2 cis of 270 degrees. So it turns out that based on our formulas for the product and the quotient of complex numbers, we do have an option of just multiplying or dividing complex numbers in rectangular form by multiplying by the conjugate. But now it turns out that we have some easier methods if they are already in trigonometric form, because all I'm doing in this particular case is dividing the R values and adding or subtracting the angles, depending on whether or not it's a product or a quotient. And therefore, negative 1/2 I is going to be in trigonometric form the same thing as 1/2 times cis of 270 degrees. Just to sum up the two actual theorems that we derived today, we see that if you have any two complex numbers, namely R1 times cosine of theta 1 plus I sine theta 1, and notice the second one has a different radius and a different angle. If we were to multiply those two together, then what we should recognize is this simply becomes R1 times R2. So we multiply together the radii. And now what's left is cosine of the sum of theta 1 plus theta 2. And the same for sine. So we simply multiply the radii and add together the angles. Ran out of room here. And another way to write that in cis form is just to realize that I take the product of the two radii times cis of the sum of my two angles. And that's the product rule. As for the quotient rule, we're going to basically be doing something very similar. We're going to be taking the quotient of the two radii. Okay, so R1 divided by R2. But now, instead of multiplying the radii, we're obviously dividing the radii. And now the only difference is that now when we take cosine of the angles, I'm taking theta 1 and subtracting theta 2. Okay, plus I times sine of the difference of those two angles as well. So now if I am taking a product, I multiply the radii, and if I'm taking a quotient, I divide the radii. If I have a product, I take the sum of the angles, and if I have a quotient, I take the difference of the angles. And therefore, the other way to write this in cis form is simply R1 over R2 cis, and now we get theta 1 minus theta 2. So this is a breakdown of the product and quotient theorems that allow us to now take the product and quotient of complex numbers without having to do the distributive property, without having to multiply by a conjugate. If the numbers are already in trigonometric form, we could simply apply these two properties to find the products and quotients.